When you type a question into GPT, Claude or LLaMA, a fascinating chain of events unfolds in milliseconds, almost like a cinematic sequence playing behind the scenes, complete with intricate choreography between mathematical structures and learned patterns. What feels to you like a simple text box exchange is, under the hood, a massive orchestration of linear algebra, probability theory, and deep learning architecture. It all begins with words becoming tokens and then numbers. The system's tokenizer breaks down your input into chunks called tokens. These could be entire words in some cases, but more often they are subwords, characters, or even byte sequences, depending on the model's design. For example, unbelievable might become 3 tokens, UN, believe, and able. Each token is then mapped to a unique ID in the model's vocabulary and passed through an embedding layer that turns it into a high-dimensional vector. This vector, often with hundreds or thousands of dimensions, encodes the token's meaning as learned from billions of examples. This is where the understanding starts. The numbers aren't random, but are carefully tuned so that similar words have similar vector representations in semantic space. Next comes positional encoding, a clever workaround for the fact that transformers, the core architecture, have no built-in sense of order. Without it, the sentence "Alice loves Bob" would be identical to "Bob loves Alice" in the model's eyes. Positional encoding injects information about each token's place in the sequence, often using sinusoidal patterns or learned position vectors. This allows the model to differentiate between a word at the start of a sentence and the same word at the end, preserving both meaning and structure. Then arrives the self-attention mechanism, arguably the heart of transformer intelligence. In this stage, every token compares itself with every other token in the sequence to determine how much influence they should have on each other. Imagine a conversation where each word can look back and forth across the sentence, deciding, "I should pay close attention to that word over there. It changes my meaning." This process happens in parallel across multiple attention heads, each focusing on different linguistic or conceptual relationships. One might detect verb-subject links, another might track sentiment, and yet another could follow long-range dependencies in storytelling. After attention, the model routes these enriched vectors through feedforward neural networks, mini processing hubs within each transformer block. These multi-layer perceptions add non-linearity, combine features in new ways, and push the representations closer to the final goal, making a meaningful prediction about what comes next. To maintain stability and prevent information loss, the architecture uses residual connections, which skip over the main processing path to reintroduce the original input, and layer normalization, which scales and shifts the data to avoid runaway values or dead neurons. This balance keeps the system learning and reasoning efficiently without collapsing under its own complexity. This entire pattern, positional encoding, attention, feed-forward transformation, residuals, normalization, is, well, stacked in dozens of layers for large models. Think of it like building up meaning in layers. Early layers detect word shapes, basic grammar, and common collocations. Middle layers, on the other hand, uncover relationships, analogies, and more abstract features like narrative structure. At this stage, the final layers come into play, integrating all the features we've learned so far into a deep, context-aware representation. This, in turn, enables the generation of output that is, well, coherent and nuanced. So, finally, we arrive at output generation. The processed sequence is now passed into a final projection layer, which, maps it back into the vocabulary space. A softmax function then takes over, converting these raw scores, sometimes called logits, into probabilities for every possible next token. The model selects the next token either by picking the one with the highest probability, which is known as greedy decoding, or by sampling based on the probability distribution for a bit more creativity. This token is then added to the sequence, and the process repeats itself until a stop condition is reached. All of this happens in mere fractions of a second, powered by massively parallel computation across GPUs or TPUs. It's a constant interplay between mathematical precision and statistical approximation, where patterns from past data are applied to produce novel, contextually relevant answers. So, when ChatGPT, Claude or LLaMA responds, it isn't blindly guessing. It's running a highly orchestrated cascade of computations, pulling on vast learned knowledge, refining context with each layer, and generating language that feels natural because it has been trained to predict human-like sequences with extraordinary fidelity. You're seeing the tip of a computational iceberg that's both elegant in design and staggering in scale.